I was asked to talk about methane specifically in the Arctic, but I'll talk about methane as a greenhouse gas, what it does, and how serious a problem it is, and then I'll talk a little more about methane in the Arctic and what it does there in the Arctic Ocean. I should note, as Daphne's already sent a message, that there was a very, very important report came out today, and I've been busy trying to make some new slides so I can show it, but I think I'll leave it to you to look at that report. It's the Global Methane Tracker brings out a report every year on now very, very much better, getting better all the time because of having more sources of satellite data on what methane is doing, how much of it is being released, and in what way. So I'd really recommend you read that Global Methane Tracker report for what's happening this very moment. So I'll give more background into methane. Okay, so methane here is we're talking about the second most powerful anthropogenic greenhouse gas after carbon dioxide. Now, I'm not sure if all the pictures, I can move them away. Yeah. Carbon, if we look at the radiative forcing, which is the impact of the gas on climate, then carbon dioxide is leading the pack, or as always, but that's the top brown bar. But methane is following along behind, and it's about 60% as important as carbon dioxide in terms of how much warming potential it has. And we can see some lower values there from the existing halocarbons. Nitrous oxide, which surprisingly is coming along quite fast, it's increasing its concentration in the atmosphere as rapidly as methane and carbon dioxide. So then we have a lot of other smaller impacts. So methane is important. It's the second most important gas, but it has a shorter lifetime. Of course, carbon dioxide was thought to be about 100 years, but that keeps going up into the thousands now. If you look at all the possible ways carbon dioxide can be released and then can get through various systems without leaving the energy system. So carbon dioxide is hundreds of years, but methane is 9 to 10 years. So we're looking at a short-term forcer of climate. So we need to treat them in a different way. Okay. I want to. There we are. I've got rid of it. Okay. If we look at the concentration of methane in the atmosphere, it's been possible to go back a long way by looking at the gas content in ice cores, in bubbles in ice cores. And we see that just like carbon dioxide, it had a value which it reached, which was the immediately post-glacial value, which in this case was about 620 parts per billion. And then as soon as the Industrial Revolution began, it started shooting up because of the production of methane during burning of fossil fuels and coal. So it shot up, and then it started to reach what looked like would be a sort of a steady value about 10 years ago. So this shows the rise to its during the period since the end of the Ice Age, and we see also that the rise in methane content is it's roughly tripled while the carbon dioxide content in the atmosphere only rose by a few tenths of %. So methane has become relatively more important as a greenhouse gas in the atmosphere than carbon dioxide. Carbon dioxide is still in the lead. And so the value has been around about 1,800 parts per billion, and which is roughly 3 times what it was before the Industrial Revolution. Now, now why does methane act as a greenhouse gas? Why does anything act as a greenhouse gas? Well, we know that the reason is that certain gases, they have to have at least 3 atoms in the molecule, and this permits a range of rotations that the molecule undergoes, which means that the molecule can absorb radiation, incoming radiation, and it acts as a damper to radiations trying to pass through it. And the reason why carbon dioxide is the biggest contributor to global warming is because the peak of the absorption band for carbon dioxide over here corresponds to the peak of the energy being emitted by the planet. If we look at this is a radiation measured from the top of the atmosphere from a satellite, and we see that Wien's law of radiation should give you a smoothly varying radiation output from the planet that goes out into space. In this case, this is the line for 7 degrees at the top of the atmosphere. But instead of following that line nicely, you get these sudden absorption bands at particular frequencies, which are due to this structure of some of the gases in the atmosphere that have 3 or more atoms. And we see that, unfortunately for us, carbon dioxide happens to correspond to the peak of the spectrum. So the absorption band, in which we see a lot of the incoming energy from the planet being absorbed before it can get into space, that is a wider and deeper band than you get for other gases. So CO2 is the most powerful greenhouse gas for that reason. But other important gases are ozone, methane, nitrous oxide, and water vapor. So methane is over here at a lower level in the Wien's law emissions, but it still has a big impact, and when it's released into the atmosphere, it forms a very constant concentration over the entire atmosphere. Its mixing is rapid, but it's not perfect. And in this case, we see a mixing ratio of the 2 hemispheres, and that there is a greater amount, a slightly greater amount, of methane in the atmosphere in the northern hemisphere than in the southern hemisphere. And the question, which is not being fully solved, but is, does this mean there are more sources of methane in the northern hemisphere producing a higher level in the atmosphere than in the southern hemisphere? And that's probably the answer to that is yes. So we look again at the changes since the pre-industrial time. These are real data points taken from ice cores, and we see that puts in some error bars as well. And we see that the big change happened during the 19th century, and the methane level rose rapidly right until the middle of this century, or the end of last century rather. And then something happened which people were happy about. That is, the methane levels seemed to flatten off. And this happened around about the year 2000. So this is methane level in the atmosphere went up to about 1780, and then it went flat. And so everybody thought, it's a bit like everybody thinks about COVID going away. You know, what a relief. Here we are. It's at least we don't have to worry about methane going up all the time. It's reached miraculously a flat level. Nobody knew why it had reached a flat level and didn't go any higher, but it did. So we thought, wonderful. And if you look in detail at the growth rate of methane in the atmosphere, we can see that right up until the year 2000, this is not a very good picture, but we can see there was a positive growth rate of about 5 parts per billion a year. And then beyond the year 2000, despite a lot of inter-annual fluctuations, the level went down to zero, here's zero, and we had a decade of roughly constant methane concentration. However, at the end of that decade, people started to note a nasty little upward trend, and it was first spotted in data from the Alps. And here we see the data points that after 2006, the level of methane started to go up slightly. It was a gentle increase, but that increase got to be less gentle. And here's a data set from a station at Alert in northern Canada on Ellesmere Island. And we see the seasonal fluctuations, but when we take those out, we get an increase starting again in about 2006 and accelerating its rise from then on. So we see a greater rate of rise in the last few years. The interesting thing here that you may notice are these little isolated points over here. Now, if you're a geophysicist of a suspicious nature, you'll say, oh, well, that's just sort of not very good observations being done. You know, when I do field observations, I get random outlying points, and you just sneakily avoid putting those into your graphs. So the trouble is, the accuracy of this system is very, very good. So these are not random outlying points, they're real data points. And Jason Box, who's a Danish scientist working on this, called them dragon's breath, which was a nice, nice phrase, because what he says is these are little puffs of methane being released from sources in the Arctic, blowing across the collector in Alert and giving you a high value for a short while. And since this is methane and methane burns, he called it dragon's breath. So it's like the source of methane is there somewhere upwind of the receiving station in Alert, and it's giving little puffs of methane which the wind is carrying across the receiver. So there are individual sources in the Arctic which are being identified here. And all in all, this acceleration that happened after 2006 has gone on accelerating, and methane, relatively speaking, is rising faster than carbon dioxide. So we don't know why the methane emissions flattened out, and we don't know why they've taken off again. There are many reasons because of the many different sources of methane, but here we are with a rapidly increasing methane content in the atmosphere. And of course, the carbon dioxide content has never ceased increasing. In fact, it's never ceased accelerating. And that's the thing that frightens me the most, is the fact that every time there's an agreement, a climate agreement, it doesn't have the slightest impact on carbon dioxide levels. And the Paris Climate Accord also has had no impact at all on the rate of rise of carbon dioxide. It just goes on increasing. And it's now being joined by methane, which is taken off as well. Now we can see that in many ways. Firstly, there are now a number of satellites which can measure methane in the atmosphere. And here we have data from a satellite where you've measured northern hemisphere methane in the troposphere in 2008 and in 2011. And we can see that the level all over the northern hemisphere has gone up in those 3 years. So where does it come from? It's coming from somewhere, obviously a number of sources. And this is a summary of where we think it's coming from, how many teragrams a year are being emitted. So first of all, let's look at anthropogenic sources, that's us. And fossil fuels are a large source. And that's when we burn fossil fuels, there's usually a certain amount of methane in those fossil fuels released into the atmosphere, and we can't really do anything about it, except that we get a lot of it is not actually the fossil fuel itself. It's actually leakage of methane from gas pipelines. For instance, this is the biggest villain here, as has been mentioned in today's report, is Russia, because Russia seems to be the biggest villain everywhere at the moment. But at the moment, it is actually the most careless country when it comes to being able to control methane emissions, accidental methane emissions from gas pipelines and other sources like that. So fossil fuels is the biggest single source. Waste decomposition down here is because when you put methane on a landfill, and the landfill, the methane, the rubbish rots away, and in rotting away, it emits methane. So the decomposition of rubbish on landfills is a large factor. Rice cultivation is surprisingly large, mainly because the rice is grown in paddy fields, and the rice itself, the leaves, sit in the water and rot and emit methane. So rice cultivation is actually, which you think of as being, a noble thing to do, feeding the world and so on, but in fact it's putting greenhouse gas into the atmosphere to quite a high level. Domestic ruminants, this is the famous cow's stomach effect, which is that the domestic animals, especially cows and also sheep and pigs, emit methane because they regurgitate their food in order to re-chew it, and so they emit a lot of methane. And because we've got a lot of domestic animals, they are actually a large source of methane. And of course, one of the things people really concern themselves with is, can we get that figure down? So vegans will say, well, we just have to stop eating meat and only eat plants. That would certainly do the job. But if you feel the need to eat meat, which most people do, there are methods which seem to have some effect on the amount of methane produced by cows. And one of them is to feed certain species of seaweed to cows. This reduces the methane produced by the cow. So there's a future in redesigning what you feed a cow with. But Adavocaat would tell you that the best way is not to eat the cow at all. And also that has the advantage that you are using less of the Earth's land for keeping domestic animals, and more of it is then available for growing plants. So there's domestic ruminants. And biomass burning is that when you get fires, which you do more and more now, methane is one of the products of the burning of trees and underbrush. So here we see 5 sources of methane. There's more than that around, 5 due to man, and so it is really difficult to sort out which ones are increasing, which ones might be decreasing, and therefore why is the total going up. That's the anthropogenic sources. Then we look at natural sources, and here the biggest single source is wetlands. And all over the world, where there is wetlands, we see rotting away of the the plants in water, and production of methane from that. And as I'll talk about later, one of those is not wetlands at all, but underwater in the Arctic. So that's a big source, but we've got permafrost, which here is listed as a very small source, but actually that's gone up much more in the last few years. Geological sources, that includes production in the ocean. There's a peculiar one here, which is that termites produce methane from their way of life in their termite hill, and that produces quite a large amount of methane. Wildfires are becoming an increasing source. Wild animals, well, there's not many wild animals left. I think you must have seen that very nice and very frightening picture, which shows that if you look at the biomass of mammals on planet Earth, there's only 4% of the biomass is wild animals, 36% are humans, and 60% are domestic animals. So if we're looking at all the living things on planet Earth, these cows are pretty dominant. If they, it's lucky they don't choose to take over the world, because more than half the mass of biomass of mammals on the planet are cows. So it's only 4% in terms of wild animals. So that produces this slice. So these are the natural sources. And then where does the methane go? Well, we know that within 9 to 10 years of emission into the atmosphere, methane has been oxidized, and it reacts with OH in the atmosphere, especially the troposphere, and is gone. And that's where most of the methane disappears to. It actually doesn't have a long lifetime in the atmosphere, unlike carbon dioxide. And it reacts with chlorine as well. And this is a technique that's being developed, iron salt aerosols, of reacting methane with ferric chloride that's based on chlorine, and that it supposedly and seems to actually get rid of methane. And this is potentially the most promising technique for removing methane from the atmosphere. It also gets taken up by the soil, and some of it gets up into the stratosphere. So this is a data set that's about 10 years old, but it just shows where methane is emitted and where it's absorbed, and the brown is changes that are due to man's activities, anthropogenic change, and the green are emissions and absorptions from natural processes. So they produce one of these every 10 years. So I've only got one here to show, but there isn't actually much difference from decade to decade. The relative quantities of methane from different sources and their emissions and absorptions don't vary enormously from decade to decade. So it's this is what we had 10 years ago, and it's more or less what we have now. The methane is destroyed in the troposphere. It's emitted into the atmosphere by wetlands more than anything else. And if we look at human sources, fossil fuels and landfills and ruminants are the three big offenders. Okay, I showed that first map that seemed to indicate a higher methane emission from the northern hemisphere than the southern hemisphere. And it seems to be the case, but there's been an analysis done by the carbon tracker of where, at what latitudes are the largest emissions. And wetlands, of course, are the biggest emitters, and we see a peak there at round about 0 degrees, because there's more wetlands in low latitudes than in high latitudes, although we see another peak at high northern latitudes, about 60 degrees, and this is from the melting, thawing of permafrost. Then, if we look at biomass burning, that also has a peak near the equator because of the lazy or unproductive practice of burning off waste from when a crop has been collected in. You burn it and produces methane amongst and carbon dioxide. Then fossil methane, that's coming from man's activities. Mid-northern latitudes are the main source because that's where cities and industry and civilization is, or cities and industry anyway. Then if we look here at agriculture and agricultural waste, again, it's the biggest peak is in mid-northern latitudes, where we have the biggest production of crops in the middle ranges of North America, Ukraine, and Europe. And then chemical loss, that's this is actually where the methane goes away, and so it's really taking away from where the production's happening, and the loss is greatest in slightly northern latitudes. Well, the problem is there's a really serious threat from the offshore Arctic, and summarizing it, it's that in fact, rather than talk through this, I'll show the pictures, that when we look at the Arctic Ocean, we find that about a third of the area of the Arctic Ocean is very shallow shelf, between 50 and 100 meters water depth. That's all the light blue here. And 2/3 is the proper deep ocean. This means that the Arctic has the lowest mean depth of any ocean in the world. But a lot of it is normal water depth, but this huge area of very, very shallow water, which during the last ice age was dry land. Now, up until the 1970s, this was how sea ice varied in the Arctic from winter to summer. This is winter, this is summer. We see that in summer, in winter, obviously, the whole Arctic Ocean is ice covered, and plus some of the surrounding seas. But in summer, nearly the whole Arctic was still ice covered. So if you compare that with the actual map of shallow water, we find that the ice edge is still very close to land. So there's a lot of the continental shelf area of the Arctic is still covered with ice, or was still covered with ice in the summer. And so the water temperature would be at or around 0 degrees. There'd be no melting of the ice going on and nothing happening underwater that could concern you. However, as the sea ice has been retreating, we now get to this position now in midsummer. This is September of 2012, which was the record retreat so far. And we see that instead of the summer being still extending almost to the coastline of the Arctic, it's retreated right to this level here. So all this big area here, which is shallow water, 50 to 100 meters deep, is ice-free in summer, sometimes for 4 months or more. And you can measure the water temperature, and we find it's quite high. I did a cruise through Bering Strait into the Arctic Ocean where I measured 11 degrees, and that's typical of sea bathing in the North Sea, not in the Mediterranean. But here we have the year 2007, for instance. We see the sea ice retreated right back to this blue line, and all of this area was ice-free, and the water warmed up because the water depth is shallow, and there's a lot of radiation during the summer. The water warms up, and here we see it reached 5 degrees C, and there's been cases since then when it's got to higher values still. Now, what happens then? Well, if you're getting several degrees above 0, and we find that even down at the seabed, the water temperature is above 0. Now, for instance, here in 2007, we find that near bottom temperatures reach 3 degrees C, and that's a temperature at which melting of frozen material can occur. So what happened is that there is, and always has been since the last ice age, a very thick layer, actually a couple of kilometers thick, of methane in the form of methane hydrates, which is a methane reacted with water to produce something that looks like ice. It's a solid, but it's stable. Now that sits there and was covered with a thin layer of frozen material, and that layer prevented methane from escaping. So we had methane hydrates in the form of solid material covered with what amounts to a pressure cooker lid. However, as soon as people started to study this intensely, and by people I mean Shakova and Semiletov, who are Russian scientists and who started this work and are still doing it, but they've been joined by a lot of German, Swedish scientists since then. But they observed plumes of methane coming out of the seabed, reaching the surface. Now, well, the first thing is these are early. This is work done by Semiletov, but recently, every year now there's an expedition goes there, and there's much more methane coming out. This is a recent ecosounder profile, and this shows really almost the whole of the shallow water region of the East Siberian Shelf has got very large amounts of methane coming out. So when you go there, you'll find a lot of methane bubbles. It quite to the point where it's quite dangerous. This can easily catch fire, and so we're seeing more and more methane. And the fear, this is the methane bubbles trapped by sea ice near the surface. This is rising to the surface, and this is the methane hydrates. Now, the methane hydrates look like ice, but because the component, this mostly contains methane, then you could set light to it. And of course, if you've seen the very nice movie Ice and Fire, which just came out last year, the cover advertisement shows a scientist surprised by the fact that he's caught fire because he stuck his ice axe through an ice-covered lake in Siberia, and methane came out and caught fire. So it's dangerous from that sense. And the amount of methane coming out, this is a sort of artist's impression, is that it's coming out from particular caverns and storage regions below the level of the permafrost. And this is a NSF's view of where that's coming from. Now, and here's some a hole in the sea ice with methane coming out. Now, that has a number of impacts. One is that the amount of methane involved is increasing year by year, and the fear that is expressed by the Russian scientists in particular, but also by other scientists, German scientists, is that the quantity could become very large. The fear could be maybe 50 gigatons a year coming out of the seabed. So it's becoming it could become a kind of burst, a methane burst, rather than simply methane coming out at not a controllable rate, but at a low rate. This 50 gigatons a year fear is the one that really is propelling more and more research into dealing with methane and trying to get rid of it. While it's there, of course, then it slows down the growth of sea ice in the autumn. And so we have here, for instance, in November, when there's normally sea ice over the whole Arctic Ocean, it turned out to be ice-free because of the impact of the large amount of methane coming up from the seabed. Now, we did with some colleagues, did a study of what would that do to global temperatures, and our work has now been taken over by a colleague from the US who's found that in fact the effect is double what we reckoned. We did an analysis of emission of 50 gigatons, and which is about 8% of the methane that's sitting in the East Siberian Sea. This is the blue here is what will happen if to global temperatures if we don't do anything much about it. In other words, business as usual scenario, this is what will happen if we inject 50 gigatons of methane. You get a difference of about 0.6 or 0.8 of a degree, which carries on. And this is going to be a very big element in a sudden warming of the planet. And we just don't know how we will cope. We're trying to cope with a warming which is accelerating, but we don't imagine a sudden warming. And this will be a sudden warming. Now, a scientist from the US Air Force in California has done a reanalysis of this, and she gets, instead of 0.8 degrees, she gets 1.4 degrees as the, and I think her modeling methods are better than ours. So I'm willing to give way to her estimate. And that's even worse. That's 1.4 degrees in one go. And she's written a paper on that, which I think is very important. We got different values for we did a financial analysis as well, which is how much this methane burst would cost in terms of how much at the moment we reckon carbon dioxide emissions cost. And we get, if we use different periods for the emissions, we're getting something like 60 to 70 trillion dollars. So that's huge. And here we see the cost per decade or per year, per decade actually, over the lifetime of a methane outbreak. And we're getting $60 trillion, which sounds a lot, but actually is only about 15% of the overall cost to the world of anthropogenic warming. So methane is still not going to be the killer, but it's going to be a killer. So this is just to say how we did that, but it's integrated assessment models.
Great. So okay. Can we wrap this up so we've got almost 10 minutes for Q&A?
Okay, well, I'll finish with this last thing here and say, this is, if you want, there's a website that gives you the global methane budget every day. So that's something that's well worth looking at. And then this is the question which you asked, what are we doing now? Is that you must have been following the work that's been done on iron salt aerosol. And that seems to be the most promising way of removing methane from the atmosphere. I mean, let's remember, we're not getting rid of methane steadily. It's not like direct air capture to get rid of carbon dioxide. We're not trying to bring the methane level down slowly. What we're doing, trying to cope with, is an emergency where there's a sudden methane outbreak, which left to itself will give us a warming of somewhere between 0.8 and 1.4 degrees. And you have to get rid of that methane quickly as you possibly can, otherwise it's causing terrible effects. So iron salt aerosol, where you waft iron ferric chloride or iron salt over the surface or over a place where methane's being emitted, seems to work, and all the experiments done so far point to that as a workable method. And then there's another method using buoyant flakes. This was where you have huge mountains of these rice husks, especially in the Far East, and if you douse them with a form of mud which is rich in iron, then they'll float about and do the same job as iron salt aerosol. And so buoyant flakes seem to be another potential way of getting rid of methane, which would work. So there's more than one method around, but it's more difficult than simply carbon dioxide removal. Okay, well, I'll finish there.